Hello everyone, this is Nash. Today we are going to solve the combination lens problem. In high school physics, usually we simply deal with a single lens and we can plug in the equation to find out where the image should be located. But now we get two convergent lenses. As you can see, one got a focal length of 24 centimeters and the second lens got a focal length of 9 centimeters. If we get two convergent lenses, how is it possible to solve this problem? It looks a little bit more complicated, right? But actually you can still solve this problem while using the high school physics. The only thing you need to do is you need to know the game rule of the combination lens problem. Okay, let's get started. First, you might be familiar with the problem having single lens, just like if there's only one lens. In order to solve this problem, the first thing you need to do is you ignore the presence of the second lens. Just imagine that there's no second lens. You pretend there's nothing on the right hand side. There's only one lens, that is the first lens. You ignore the presence of the second lens. This is the trick. Okay, so if you get purely one lens, if the problem simply get one lens and the focal length is 24 centimeters, you can first draw the ray diagram. And my favorite two rays is you emit two rays from the tip of your object. And the first ray is now parallel with the axis. And when they hit the lens, it's going to be converged to the focal point of the first lens. And my second favorite ray is now going through the center of the lens. Since it's a quite thin lens, so you don't need to you don't need to worry about the deflection, so it will just go straight through the center of the lens. And usually if you get a real image, you will see the two rays are going to meet with each other. They are going to hit the same point, and the same point will be the tip of your image. This is how we find the location of our image. But now it's now diverged. There's no cross point, so that means you will no longer get a real image. But however, your eye is on the right hand side. You can still trace the light, you can still trace the ray, and back to the left hand side. And there should be a fictitious point, an imaginary cross point, a fictitious point, and the point is the tip of your image. And how to find out the exact position of our first image, we need to use the equation. The 1 over P plus 1 over Q is equal to 1 over F, and the F is the focal length, of the lens, and P is the image, is the object distance. For example, we got a blue arrow. This is our object. It's now 6 centimeters away from the first lens, so this P is now 6. And I want to find out the exact value for our image. So let's plug in all the value in this equation. So the first step is the 1 divided by the object distance, that is positive 6, and plus 1 over Q. The Q is the first image distance, is now equal to 1 divided by the focal length. The focal length is positive 24 centimeters. All right, so turns out that we got a image distance, and the image distance is minus 8. It's minus 8. The value 8 means you are 8 centimeters away from the distance. Away from the lens, and there's a minus symbol. The -1 means you got a virtual image. All right, you got a virtual image. Let me grab a yellow pen. The minus tells you that you got a virtual image, is not real, because as you can see, the two rays, there's no cross point for the two rays. There's only a fictitious cross point on the same side of your object. So we got a virtual image on the left hand side, on the same side of the object. And the distance away from the first lens is 8 centimeters. All right, we can even further calculate the magnification, the magnification is actually the image size divided by the object size to see, let's see how much you are now being enlarged. But now, since we know that the size is proportional to the distance away from the lens, so it could be replaced. We can replace the size of the image and object and simply write it down as the distance. If we want to see how much the image is now enlarged, I can put the image distance on the numerator and put the object distance on the denominator. So that is Q1 divided by P1. All right, and the Q1 is now -8, and P1 is the object distance is +6. So we got the final value is -4 thirds. -4 thirds. As you can see, this value is greater than 0. The 4 thirds is greater than 0. That means your the size of your image is now being enlarged. It is bigger than your object. And the minus tells you, it's a +4 thirds. And the positive form means that you got a image which is now pointing upward. It's not inverted. It's not an upside down real image. It's a virtual image which is now pointing upward. This is what the positive value can tell you. All right. So here's the interesting part. All this problem with a single lens could be easily done by a high school student. But if you get two lenses, so here's the trick. So here's the most interesting part. To solve the combination lens problem, we first ignore the presence of the second lens. Okay, now you need to consider the second lens. So the trick is, I'm going to take my first image. I'm going to take my first image as the second object to my second lens. All right, one more time. I'm going to take the first image. As our second object relative to our second lens. All right, so I'm going to have an object distance of 8 plus 10. 8 plus 10, so I got a P2. The second object distance is 8 plus 10, which is now 18. So that is the trick. We're going to take the first image as a take the first image as a second object relative to the second lens. And the most interesting part, what is even more interesting, it doesn't matter your image is real or virtual. Once if you are now standing on the same side as your object, if you want to plug in the equation, then the object distance should be greater than 0. It should be a positive value. Even though it is a virtual image, it's not even real. So on the contrary, if you got a real image on the opposite side, even though it is real, but if you're on the opposite side, when you try to plug it in the equation, the object distance should be smaller than 0. It should be a negative value, even though it is a real image. So let's go back to the original problem. Now I got a virtual image. It's not pointing upward. I know that, but you are now standing on the same side, and the GAM rule tells you that if you want to take the virtual image, it doesn't matter it is real or virtual. If you want to take it as a second object, and the object distance should be a positive value, even though it is virtual. All right, and on the contrary, if you're on the opposite side, even though your image is real, and your object distance should still be a negative value. It's not hard to accept this concept. It's not that hard to accept this GAM rule, because your eye is on the right hand side and the light is coming from the left hand side. So there's no way for an object standing on the right hand side, So even though the image is on the right hand side and you want to take the real image as the second object relative to the second lens, then the object distance should be smaller than 0. It should be a negative value. In the future, I can give you some example like this. But let's go back to our original problem. I got a virtual image is now standing on the same side of our object. It's virtual, I know, but if we want to take it as our second object, then the object distance is positive value, is positive 18. So let's just plug in the equation one more time. I'm going to take the first image as the second object relative to the second lens. 1 divided by positive 18 and plus 1 over q2. q2 is our final second image, which is equal to 1 divided by the focal length of our second lens, that is 9. So simply by calculating, and turns out that the q2 is positive 18 centimeters. Is positive 18 centimeters. Since it is positive, is greater than 0, so the final image should be a real image. This is the gamma rule. If the final q is somehow greater than 0, so that means I got a real image. And the real image should be located on the opposite side relative to your object, and it's now 18 centimeters away from the second lens. 18 centimeters away from the second lens. So I know I got a real image. If it is real, that means the final image should be inverted. Is upside down. It's upside down. So where the location? The location is 18 centimeters away from the second lens. Like right here. So this is our the second image, which is now pointing up downward, is an inverted image, is upside down, and we can further calculate the magnification. Let's see how much is now being enlarged relative to our second object, which is actually our first image. And the second magnification is q2 divided by p2, and q2 is 18 centimeters. q2 is 18 centimeters, and p2 is the second object distance is 18 centimeters. 8 and plus 10 is 18 centimeters. So the value is -1. So the 1 means that the image is not bigger. It's the same size as the second object, as the first image. And the minus tells you that it's an inverted image, is upside down. So if we get two magnification, this first magnification and the second magnification, now we can further calculate the total magnification is m1 times m2. m1 times m2 is positive 4/3 and times -1, which is -4/3. That means your final image is somehow bigger than your original object. Then the minus is now telling you that you get an inverted image. It's now pointing downwards. It's upside down image. It's even a real image. So you might be curious, how is it possible if we ignore the presence of the second lens, we get one lens, and there's no cross point, there's no real image, only got a fictitious cross point, we get a virtual image. So how is it possible? The final result tells me that we got a final positive image distance. That means I got a real image, and the image is now even being enlarged, is greater than the object, it is bigger than the object. So how is it possible we get a real image ultimately? We can still try to analyze, accept the final result by correct the two rays a little bit more. Let's consider about the presence of the second lens. It's also a convergent lens. So it will keep continuing converging the two rays even more even more, so I use the red pen. This is the original first ray. It's not going to hit the second lens. The second lens is a conversion lens, so it will keep converging the ray a little bit more like this. And for the ray that goes through the center of the first lens, it will be converged by the second lens even more. So this is the cross point. They're going to hit the tip of our final image. So this is how we use the ray diagram to find out where the location of our image should be. But if you don't know how to draw it, you can simply by using the equation. And the truth is, if you want to take the first image as the second object, the only thing you need to worry about is you need to make sure it is on the same side of your object or it is on the opposite side of the object. If it is on the same side of your object, it doesn't matter if you are real or virtual. The second object distance should be a positive value. If you're on the opposite side, even though it is a real image and the object distance should be still smaller than 0, it should be a negative value because your light is now coming from left hand side and your eye is on the right hand side. Okay, so this is how we solve the combination lens problems. Hope you like it, and thanks for watching, and this is Nash.